Okay, welcome to EE210B. This is a class dealing with inference over networks. Hopefully you are going to learn lots of interesting things in this class. Okay. It deals with the study of information processing over networks. How do we design algorithms that let agents that are connected by some topology work together to solve adaptation problems, learning problems, optimization problems in an effective way. Okay, I'm going to give you more details about the objectives of this course. This first lecture motivates the topic and gives you a general overview of what the course is going to cover, what references we are going to use, and so forth. You have access to the class website as well, and I have some handout information there. Okay. So moving forward, okay, if you go to my research group's website, and I have the link shown up there, under publications you will find a link that allows you to download the PDF file for the lecture notes for this class. Okay, you can access them also on, I believe, on the library's website. You should be able to download or access these notes, but you can also download them on this website. And for any information about the class, of course, you can always write to me and reach me by email. It's that first book on the far left that we will be using in this class. Okay, so this is a list of the references that I will be using for this particular course. This is a collection of articles. These particular ones happen to be survey articles. They cover different aspects of the topic, and they give references to many other works that are relevant to the area, okay? And they bring the material into a unified framework, so it makes it easier for you to understand. The first reference, that's about a 500-page manuscript. That manuscript is the text for this particular course. Okay, I will be following it to the letter. The second reference, the article in the Proceedings of the IEEE, is essentially a summary of that book. Okay, that's essentially what it is. So if you want to have a quick read of what we are going to be covering in this course, not all of the material here appears there, but it gives you an idea. Okay, for example, most of the proofs do not appear there, and some other topics also do not appear there. And I also have an article in the Signal Processing magazine, which is more accessible. Okay, and there is another chapter down there, which will be useful when you try to solve some homework problems. Okay, anyway, so these are the references. For the first reference, again, if you go to the website link I showed you earlier, you can download it from there. Okay. And that's allowed. The publisher allows you to do that. You can also access it on the UCLA library website. Okay, that's what I'm told. Okay. Now, if you are interested in having a hard copy, then you will have to buy it. Okay, so that's how it works. Okay. Now, for you to get the most out of this course, you need to know some basic background material. Okay, so you need to know your probability, what random variables are, what variances are, what covariance matrices are, right? You need to know that material, okay? So what correlation is, what independence is, and you also need to know your linear algebra. Okay, and I give here list some of the concepts that we'll be using in this class. If you took 210A with me last quarter, which deals with adaptation and learning by single agents, in this course we are going to be talking about adaptation and learning by multiple agents. Okay, you have seen some of these concepts, but in this lecture today, starting today, I'm going to be reviewing some of these concepts. Okay, so this lecture and the next lecture will be background material, so that at least those who may not have seen this or do not remember much of this will see it again. Okay, so you need to have some training in this material to be able to follow this course. Okay, so if you don't have it, then make sure to follow the first few lectures in this course as closely as you can, and read the appendices, the references that I'm going to give you, so that you catch up with these topics. Okay, so that's the background material. Now, the way I organize this course, it's divided into 5 main parts. The first part is background material. Some of you may get bored because you already have seen it, even though I'm going to be covering some new topics that you may not have seen, even in 210A. Okay? But some of the material may be, you may have already seen it, but that's okay. You will see it in the context of the information I need for this course. The second part of the course will deal with single agent adaptation and learning. This goes beyond what we did in the 210A class, the adaptation and learning class that you attended last quarter. Here you are going to see additional results, more general results, but all focused on the single agent case. In the third part of the course, I'm going to be talking about centralized adaptation and learning. If you collect all the information in a single place, in a fusion center, what's the best performance you can expect from a solution that follows that architecture? And how does it compare to the single agent performance? A single agent working on its own, trying to solve an adaptation, a learning, or optimization problem, how well does it perform compared to a centralized solution that collects the data from many different sources? And then in part 4 and also part 5, we'll move much deeper into network information processing. What if I now have a network of agents trying to solve these problems and cooperating over a certain topology? You don't have a fusion center anymore collecting all the data. All the interactions are localized. What kind of models are we going to use to study mechanisms like that? And what kind of strategies are we going to develop to allow these networks to learn well and efficiently, right? So that's what I'm going to cover in part 4 and part 5 of this course. Okay, so under part 5, which covers a large portion of this class, you are going to learn about different cooperation strategies, benefits of cooperation, and different approaches to distributed signal processing, and also distributed optimization problems. Okay, so these are the 5 main parts of the course. Okay, so let me now give you a very quick short overview of the course. Okay, a quick motivation before we start with part 1, which deals with background material. Okay, so that's the high-level description of the course. It deals with the topic of information processing over graphs. Okay, so I'm interested in studying networks of agents that are interlinked by some topology. They share information only locally. Every agent has access to information from its neighbors or a subset of its neighbors. And through localized interactions, I would like to develop algorithms, strategies that allow these networks to solve adaptation problems, learning problems, and optimization problems in a very efficient manner, right? So for example, if every agent in this network has access to some pieces of information, if you take all these individual pieces of information and collect them somewhere and you solve a learning problem, let's say a pattern classification problem, you will attain a certain level of performance. But if I don't have that luxury of collecting all the data at a remote location that can perform that processing for me, if I can only process the data locally through localized interactions, can I make a network of agents like this, even though each one of them only has access to part of the data, achieve similar level of accuracy to what a centralized solution will perform? If I can do that, that would be something very interesting to achieve, right? So that's one of the objectives in this class. You're going to learn how to do these things and whether they are possible or not, and what problems come up if you try to do it, okay, and what challenges we face, okay, if we try to do that, right? Okay, thank you. So moving forward, okay, so this is what you are going to learn, high-level description of what you're going to learn in this class. You're going to be able to compare different network configurations to each other. Is it better for me to use this particular topology or this other topology? Does it make a difference which topology I use? That's an important question, right? How do I compare networks to batch solutions or centralized solutions? Can I make a network approach the performance of a centralized solution? Right? Can I make a group of agents working individually within their neighborhoods perform as well as the centralized solutions? What's the best performance I can hope for? It's always important to understand limits of performance in these problems, right? And does it always help to cooperate, to work with others? Okay, you are going to see that sometimes the performance may go down for certain reasons you are going to understand, okay? And when you put agents to work together over a network, some interesting phenomena come up and that are specific to the network structure, and I'm going to highlight them throughout this course. For example, if every agent is able to solve a learning problem or an adaptation problem, is able to estimate something in a stable manner, and if I connect them by a network, and I now ask them to solve the same problem by additionally interacting with their neighbors, will it always follow that if the individuals are able to solve the problem, the network can solve the problem? And the answer is that it depends on how you ask them to cooperate with each other. The cooperation protocol will influence whether the group will remain stable when the individuals are stable. Right? So some interesting phenomena are going to come up, which the analysis will highlight. Okay? So this comes back to the question I showed you before. If I'm interested in solving an estimation problem, or I'm trying to solve a pattern classification problem, and I have many structures to choose from, many networks to choose from, which topology would you choose? Or does it make a difference? Right? Does it really make a difference? Or can I make each one of these topologies perform as well as the other? These are questions that we are going to answer in this class, okay? So this is just one particular aspect that you are going to learn in this class, okay? And in the process of answering these questions, we are going to consider applications. I'll be giving you examples from many different areas, and I list several of them here: distributed sensing, intrusion detection, distributed estimation, online learning, pattern classification, clustering, optimization, and multi-agent systems. These are examples that will come up as we study these questions, okay? So let me give you some examples. So this course, like I said before, will deal with information processing over networks, okay? So first, let me define what distributed processing is. Of course, there are many definitions for this term. This is one particular definition that's good enough for us. Okay, so distributed processing means, right, the discovery of global information from interactions at a local level, from local interactions among agents. Okay, that's what distributed processing is. The individual agents, as you see in this particular animation here, you have a collection of agents. Each one of them has noisy observations of the distance and direction to the target. So they interact together to improve their estimates of where the target is and move in that direction. They also have noisy estimates of the distance and direction to danger. Could be a predator, right? So they have to work together, even adjust their topology. It's not just a matter of improving their estimate of where the target is, but even adjusting their topology so that they can solve a problem like this in an efficient manner. This is just one example of behavior that you'll be able to produce using the algorithms that you are going to learn in this class. So you observe here that a distributed solution in general will consist of a collection of dispersed agents having some common objective. You can also talk about network solutions where agents may not have common objectives, or they may aim, there may be some commonality, but there also may be some differences in their objectives, okay? But for now, we'll focus mostly on the case when the agents have some common objective, and the processing is being done in network. These agents are not sending the information to some remote sensor to tell them in what direction to move, right? And they are dispersed, as you can see there. So these properties will repeat themselves whenever we study distributed solutions of this type, okay? Now, compare this to a centralized solution. A centralized solution if these nodes are collecting information, they are trying to estimate, for example, they are trying to track a flying target. Each one has an estimate of the distance and direction to the target. They can collect that information and then transmit it to a fusion center. The fusion center fuses the information, estimates where the target is, and then tells everybody else, this is where the target is, and then you keep repeating this process, right? So that's a centralized solution. Okay. Now, the problems from the perspective of distributed processing, some of the problems that you face in a centralized solution like this is, first, the cost of communications. At every iteration, you have to send data to the fusion center and collect the data back from the fusion center, right? So there is a cost associated with that. Okay. There are also privacy and security considerations. You may have applications where agents may not be comfortable sending private information, right? Or for other reasons, security reasons, sending information that's collected at a remote fusion center and then you receive it back, right? So there are reasons for you to try to limit the range over which information is being transmitted. And above all, an architecture like this has a serious problem, right? If the fusion center fails, then that's it. You cannot function anymore. Whereas a distributed solution, as you're going to see, it has a certain robustness in it. If an agent fails, you still have a network, right? The other agents can still help solve the problem. Here you have a robustness issue that is serious, okay? So why are we interested in distributed processing, right? There are many good reasons for the interest or the peaked interest in distributed processing or in networks in general, right? People talk about social networks, biological networks, transportation networks, communications networks. There are all kinds of networks nowadays, and there are many good reasons why you would be interested in performing distributed processing. I already mentioned some of them. For example, because of privacy and security considerations, you would like the processing to be performed locally rather than transmit the information remotely. There is also the convenience of having agents work together to solve more complex problems, right? The power of cooperation, especially when you have huge amounts of data. It helps to have agents focus on different parts of the data and work together. And today, it's not uncommon for the data to be already available in a dispersed fashion, right? You have the cloud, and the data is dispersed over the cloud, so it's already available in that convenient manner. And there are many useful applications that can follow from the study of distributed strategies. For example, the development of robotic swarms, right? Swarms of robots, intelligent agents that can coordinate their motion with each other and explore some spaces of interest and so forth. So there are many good reasons why you would be interested in understanding this topic in some good depth. And there are many examples in nature, right, that tell you that there is a lot you can benefit from coordination among agents. Right? There are many good examples where you have limited interactions among agents helping the network as a whole solve some complex problem. For example, I'm going to be showing you some videos very soon, right? Fish are very good at schooling together, right? Moving together. And then when they sense danger or a predator attacks, the school of fish opens up, lets the predator move, right? And then they regroup and continue their schooling behavior. So you observe many examples of intelligent interactions happening among agents of limited abilities and the network as a whole showing complex behavior, right? Complex behavior. So there are many important examples or encouraging examples of the power of coordination that you encounter in nature, and these are just some of the examples, whether it is connections within the brain, whether it is animal groups behaving together, right? Here I have the example of fish schooling. Also, ants are very good at coordinating behavior with each other. Now, one of the earliest algorithms that helps illustrate what you can do with distributed processing, just to get a little bit more technical so that you see where we are going, is the consensus construction. This algorithm was proposed in the mid-1970s by Dick Groot. You have the reference in my notes. We'll be studying it in greater detail later in this course, but for now I just want to motivate it, just to show you what you can do with distributed processing. Let's consider an example like this. You have agents, X1 through X6, 6 agents. They are connected by some topology, right? And on the links between any two agents, you have weights. So let's look, for example, at the blue agent, this agent here, which I'm going to mark with an X. This agent is connected to 3 neighbors, right? To X1, to X2, and to X4. In a network topology, it will generally be the case that each agent assigns weights to its neighbors. For example, this is the weight, this is a positive number. Sometimes it can be 0 if you want to ignore information from that neighbor. So this is A13, this weights any information coming from X1 to X3. Okay, that's what 13 means. Okay, this is the weight from 2 to 3, this is the weight from 4 to 3. Okay, so that's how we are going to define a topology, and we will talk more about topologies later. Okay, so X3 is going to assign weights to its neighbors, and this is the problem I'm interested in solving. I assume each one of these sensors, for example, is measuring the temperature at its location. Okay, they are over a large geographic area. And what you would like the sensors to know, you would like them to know what the average temperature in that area is. Of course, if you could send all the temperature measurements to a fusion center that averages these values and sends them back to the agents, that would solve the problem. But that's not what we want to do. We want every agent to work exclusively with their neighbors, and through an iterative process, they end up knowing what the average temperature across the entire network is. That's what we would like to do. So what the consensus construction does is the following. Let's look at agent 3. Agent 3 has neighbors. So N sub 3, that's the neighborhood of agent 3. The neighborhood of agent 3 here consists of agents 1, 2, 4, and agent 3 as well. Okay? So what agent 3 is going to do, it's going to combine in a convex manner the measurements of its neighbors. So it takes the measurements of its neighbors, X sub L, multiplies by a coefficient A. Okay, so these A's will add up to 1. They are non-negative numbers that add up to 1. So that's a convex combination, okay? So let's say, for example, X3 may assign 1/3, 1/3, 1/3. The weights are 1 over 3, 1 over 3, 1 over 3, and 0 to itself. Okay, that's an extreme case. Or 1 over 4, 1 over 4, 1 over 4, 1 over 4. Because they are 4, right? So these weights could be 1 over 4 each. Or you can assign more weight to some agents and less weights to other agents. What you can show is the following, and we are going to prove this result later. Every agent averages in a convex manner, right? This is a weighted average, the measurements of its neighbors. And every other agent in the network does the same, right? So that's one iteration. And then you repeat. They average these updated measurements, and every other agent does the same thing, right? So if you keep repeating this process, you can show that all of them will converge to the average from across the network, okay? Even though each one of the agents is only examining the information from its immediate neighbors. And the reason why you are able to do this is that in the first step, agent 3 sees the information from 1 to 4, but in the second step, the information that agent 4 is feeding to agent 3 will contain in it information that came from its neighbors, right? So through this propagation mechanism, information ends up spreading across the network, and you get a result like this, right? So this is a very useful algorithm for computing averages over networks in a distributed manner, right? By iterating this recursion a few times. You understand it? Of course, an algorithm like this got the attention of physicists, biologists, and even the entertainment industry, and they used it to model flocking behavior, swarming behavior, animal group behavior, and you see some instances of it even in movies. For example, in the movie The Lion King, this image here is using this algorithm, right? Every agent is sensing the velocity vector of its neighbors, and it adjusts its velocity to the weighted average of the velocities of its neighbors. So each other agent is doing the same thing. That's a consensus construction, and they end up moving in coordination like that. Of course, you have some noise added for an additional effect, but that's an example of an application of this strategy that you see here. Okay? But now there are some issues. That's very good. It's important to do that, but you find many examples in nature and many applications that you are interested in. You are not really interested in solutions where agents work together all the time and try to mimic what others are doing and converge to a consensus state. We are interested in more involved solutions. We are interested in solutions that allow agents some room for adaptation and learning, and some room to react to local information. My neighbor over there does not sense a shark near him. I'm sensing a shark near me. Should I continue to behave in agreement with him? Right? I should have more ability to respond to what I'm seeing in real time, not always in sync with what others are doing, right? So this is an example here. Here you have a network, right? All these fish and some predators, right? And you can see how they behave in a very coordinated manner to avoid the predators. So this is not an example where they are trying to get into agreement, right, into consensus. Actually, they are trying to move away from agreement, right, and open up the space for the predators to move. So biological networks in general show you that in some more complex situations, what you are really interested in is add a level of cognition, adaptation, and learning ability to the agents so that they can respond to local information faster than they would be if you limit them always to respond in coordination with other agents. You understand what I'm trying to say, right? Okay, by limiting them to respond in coordination with other agents all the time, you may be limiting their reaction time, their learning ability, their adaptation time. So this is one issue that we will be addressing, okay? And the second issue is that interactions, and these biological networks show you that interactions have to be based on how much information you have. Some agents are more informed than other agents. So you may need to give more information, more weight to information you receive from some agents than other agents. In this particular example simulation here, you'll see that as soon as two fish at this corner take a sharp turn, all the other fish follow, right? Follow quickly and change the direction of motion, right? How did they do that? If they were just trying to move in agreement with their neighbors, the majority of the neighbors, right, were moving in a certain direction that would supersede whatever reaction you get from these two. So something else happened here, right? The fish ended up giving much more weight to the behavior by the two fish that you have on the corner here, right? So interactions have to be information aware. But then that raises another question. How do I measure how much information you have relative to what I have about something that both of us do not know? We are trying to estimate, right? So this raises important questions of that kind. Yes, a question.
How well does this theory apply to a situation where each agent is trying to estimate its own objective function?
Yeah, we'll talk about this later, right? I made a reference to this, that most of the time here we are going to focus on this situation where agents want to work together, okay? But there are situations where some agents may have individual cost functions or individual objectives, right? So how do you reconcile that? That gives rise to other issues. I will be talking about this more later in this class, and then I can give you also references where you can go deeper into that, okay? Okay. So that's an introduction. So motivated by all these discussions that we had, what we are going to be doing in this course is studying adaptive networks. These are networks that consist of adaptive agents, agents that are able to learn and adapt, that are able to cooperate with their neighbors. So cooperation is limited to local neighborhoods. Even the topologies can change, but we are not going to be doing that only for the purpose of doing that. We would like the network to solve some meaningful optimization problem. For example, every agent may have a cost function J sub k for agent k associated with it, and you would like to minimize some aggregate cost function, but subject, for example, in the general case, to some constraints, inequality constraints or equality constraints that are node dependent. So this is a general problem formulation. In general, it will be a convex optimization problem that we will be dealing with. So how do I design strategies that allow agents to solve a problem like this and converge to a solution, even though every agent is limited to knowing only its own functions and its own data and neighbors, right? So this is one of the questions we are going to be studying, okay? Now, by the time we are done, you will be able to produce behavior like this, design networks that behave in this manner. For example, this is a network using exactly the algorithms you are going to learn in this class. In this particular case, my network of agents has a static objective, move to the square that may represent food, and also avoid a predator that's a dynamic objective, right? And you can see in this particular case the topology is part of the solution as well, right? Adjusting the topology. So this is a truly adaptive network. Not only the estimation and the processing is adaptive, even the topology is adaptive as well. This is one example of things that you'll be able to do. This is another example of things that you'll be able to do. For example, have networks work against each other. In this particular case, you have two networks. The blue network wants to reach the target, and the red network, right, is tracking the center of gravity of the blue network. And this kind of behavior, by the way, you observe in nature. So the algorithms you are going to learn here will allow you to design networks that have this type of cognition in them. Okay, this is another example in the context of cognitive networks. For example, you have primary users that have preference for using the available frequency bands, and you have secondary users that can jump in when some frequency bands are available. In this particular solution, we model the secondary users as agents, actually as swarming birds, for example, that look for empty bands and they swarm and they move to these empty bands through a process of distributed estimation. They work together to estimate the empty frequency bands in a distributed manner, and then they move and position themselves, as you can see in this animation here, in these regions. Okay, this is done in a distributed and dynamic manner as well. Okay, and there are many examples. For example, this is another one. I'm solving here a convex optimization problem. Okay, so the constraints define a convex region, right? And your solution is there. The minimum of the aggregate cost will be inside that convex set. So we are going to develop algorithms that will allow these agents to converge to the solution, even though every agent only has information of its own constraints and of its own cost, number one. And the solution will allow the agents to even track where the minimizer is going when these constraints are allowed to change with time. Okay, that's part of the adaptation and learning. Okay, if you have a food source that's moving, a predator that's moving, you would like to have solutions that not only go to where you want it to go, but are able to track changes in the environment as well. Okay, and one final example, dictionary learning. For example, let's assume that I have a measurement X, let's say an image, and you vectorize it, put all these pixels into a big vector, okay? Or it could be some piece of text, and the vector X of T could be a representation of how many times different words are repeated in that text, right? The way you construct feature vectors. What you have here is a dictionary. Each column, for example, could represent a word, and each row could represent a topic. I'm just giving you an example, okay? So for example, let's assume the first row is sports. And then you will have words here related to sports, related to politics, relating to the economy, right? And each entry here will tell you how often, let's say, the word ball appears under sports in an article dealing with the sports, right? Or the word Congress appears in an article dealing with politics, right? How likely it is to appear, right? So the entries here would be measures of relative frequency for the different words and different topics. So what you would like to do, I give you an article represented by a vector x, and I would like to find a sparse representation of that article. So many of the entries here are 0. That's what these colors mean. A sparse representation of that article in terms of the topics or the words that you have there, so that you know, right, in an automated manner that this article deals with politics, or this article deals with the sports subject matter, and so forth, right? So how do I solve a problem like this in a distributed manner? So you can see here I highlighted separately different columns, right, calling them sub-dictionaries. For example, I have a situation like this where different agents have access to different parts of your dictionary. For example, if X is an image and you're trying to recognize what image is that or what person is that person, different locations may have their own dictionaries, but they don't want to share these dictionaries. So these Ws are local. Right? One particular agent observes an article or observes an image, and you would like, in a distributed manner, for all the agents to be able to detect or identify what kind of topic is this article dealing with, or what kind of image is that image, through localized interactions without having to share the full dictionaries, because these may be huge dictionaries, right? This is an example where huge amounts of data may be distributed over the network, and you don't want to share them either because of the size or for security reasons or privacy reasons and so forth. So you would like to express X as a linear combination of the columns of W. Again, how do I solve a problem like this in a distributed manner, right? So these are the kinds of problems that you are going to learn how to solve. The optimization problem I showed you earlier, right? This is, of course, is a very general problem formulation. And you saw in 210A, Adaptation and Learning, the course that dealt with single agent adaptation and learning, how many problems in adaptation and learning are optimization problems of this kind. So once you learn how to solve optimization problems of this kind in a distributed manner, you'll be able to apply them to many different extensions over networks, right, of the problems of that kind, right? Okay. So these are some of the questions that we will need to address. Okay, so for example, what type of strategies should I use over networks to enable them to learn and adapt in a distributed manner? And how to ensure that the network will remain stable and behave in a stable manner, right? This is a very important question. What kind of performance I can expect? How close does the performance get to the centralized solution? Is it always helpful to cooperate and work together? So these are all questions that we are going to give analytical answers to. By the end of this course, you will be able to put a yes or a no next to each one of these answers. I'm not going to tell you what the answers are now, right? So that you continue coming to the lecture. But by the end of this course, you'll be able to give an emphatic yes or no next to each one of these questions, okay? Very good.